All right. Well, guess what? It's April. Oh my God. Is that possible? Yes. And in addition, it's the opening day of the baseball season. So we have a lot to celebrate here. But in the meantime, we have a lot of work to do today. Um, so we're, of course, in chapter 11 right now. And we're discussing probability theory. Yes, it's April. Why? Do you hate April? I don't know. I kind of like it, especially because the baseball season starts. That's a very exciting time of the year. Plus, the weather typically starts to really improve. So we could probably put away the winter jackets for real. Yeah, March was kind of, it went by pretty fast. I'll agree. Since we're all trapped inside, it's just not normal. It's not normal times. So, we lose track of what's going on. Our normal routines are very much disrupted. So it is very strange what's going on right now. Hopefully by the fall, that'll be back to normal. We'll see about that. All right. Well, anyway, so we're looking at our discussion right now is on probability theory. We're in chapter 11, and it just so happens that we've got some pretty cool videos to watch today. And so first, I just want to quickly remind everyone that we were looking at arrangements. Remember, we talked about the cars, parking the cars in the garage. And we determined that the number of ways to park the cars is 6. We can do that one of 2 ways. We can just write them down, or we can use our factorial operator, which we introduced down here somewhere. Yeah, hold on. It's down here somewhere. There it is, factorial. Okay, so in other words, the factorial operator will tell us the number of ways in which n objects can be arranged. So in the case of the 3 cars, we can see that 3 factorial is 6, which is the number of ways of arranging 3 cars. We also then introduced, no, not yet. They're so close. The problem is I don't do them all one at a time. I do them like section by section. So they all have to be done before they're ready. But it's very close, very, very close. But anyway, then we also introduce permutations where we select objects. Oh, the next midterm in about maybe 2 weeks or so, maybe not even. The next one is very short because it's only based on chapter 8. So first, before we do that, we have to review as we always do, and then we can have it. So I would say not next week, but probably the week after that. Okay, and again, it's only the one chapter. So it will be a little bit quicker than the one we just finished. All right. So permutations, with the case of permutations, we're not arranging objects. What we're doing is we're actually selecting objects. And we're choosing them in such a way that the order of which we select them matters a great deal. So before we do that, though, let's take a look at some of these videos that I was saying earlier. There's one in particular that is an interesting application of the factorial operator. And remember, the way this factorial operator works is that you start out with 0 and 1 factorial are just equal to 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. And you can see how the pattern develops. 4 factorial is, of course, 4 times 3 times 2 times 1, and it works its way up. And you notice, too, that these numbers get very large very, very quickly. So we tried, for example, 10 factorial, which turned out to be more than 3 million. And then we tried 30 factorial, and that turned out to be 2.6525 times e to the 32nd, or in other words, times 10 to the 32nd, which is an astronomical number. So the video that we're about to watch directly involves arrangements, but in a very interesting way. I think you'll agree. So let's do that first. And so hold on, let me send you that link. All right. It's called How Many Ways Can You Arrange a Deck of Cards? And when they say arrange, they mean literally arrangements like we've been discussing, where you just change the order of the entire deck. Okay, so let me put that up there. And let's check this thing out. I think you'll find it is a lot of fun.
For my real kids delivery, I told you
Okay, so was that fun or what? It's pretty staggering to think about that there's so many possible arrangements that if you were choosing different arrangements from the day of the Big Bang, you still would not have gotten through all of the possibilities by now, and there'd still be millions of years to go before you got through them all. Yeah, it does make you think how big combinations really the arrangements are. So yeah, that's right. Every time you shuffle the deck, it's possible you've created a completely new arrangement of the cards that's never happened before in the history of the universe. That's pretty staggering to think about. And of course, I think they also did a very good job of explaining how factorial works with the people sitting in the chairs, because you can see that you start out with four people. Four people could sit in the first chair, three could sit in the second, two could sit in the third chair, and one more person. Well, if you're bad at shuffling, yes, you might come across a combination or an arrangement that you've seen before, but it's also possible that you've come up with one that's never, ever, ever happened before, too. But it's just a very interesting concept that there's so many possibilities that you're not likely you could very well have one that's never been seen before. Okay, but anyway, now there's one thing I did want to mention, and I don't remember if we went over this or not. um Hold on one second. When we were calculating the arrangements, did we use the calculator to do this? Yeah, we must have, because I see it's written here. I just want to remind you that if you look at your iPhone, there is an actual factorial button on there somewhere. Let me just go look and let's see, where is it? If you wanted to know, for example, how to calculate 10 factorial, the button is in the, where is it? There it is. If you look in the extreme bottom left-hand corner, you'll find this X factorial button. And the way it works is all you have to do is hit the 10 in this case and the factorial button. You don't need the equal sign, and it will show up as what you're seeing here, 3,628,800. So the iPhone does have the factorial operator built into it. Otherwise, imagine how long it would take. You'd have to sit there and say, all right, 10 times 9 times 8 times 7, all the way down to 1, which would be quite a hassle. So it is there, which is very nice. It's just if you haven't seen it before, it's in the bottom left-hand corner. All right. And so if you hit the 30 factorial and then the factorial button, you'll see that this number is so large that the calculator actually flips over into scientific notation. You can tell because if you look at the end of all those digits, it says E32, which is shorthand for multiply this number by 10 to the 32nd power. And then, I mean, if you want to double check what they said in the video, if you hit 52 factorial, it is 8.06 times 10 to the 67th power, which is beyond astronomical. I think that that's probably more than the number of atoms in the universe. It's that large of a number. All right. Well, anyway, so that was fun. Now, there's one more video here that I want you to see, which is kind of interesting. It's a little silly, but it's kind of fun. And so let's get this going. It's called The Last Banana. So like I said, it's a little on the silly side, but it's very useful, very interesting to watch. So let's check this one out too. All right, well, that was kind of fun. That actually refers to something we're going to be doing later on in this chapter, but it was kind of an interesting way of seeing how we calculate probabilities with certain events that are repeated, like the roll of a dice. How do they have dice? Well, somebody had it, I guess, in their pocket when they crashed on the island. That's what we have to assume. That's the one thing they managed to remember to bring with them. They forgot everything else, but they managed to get those dice. That's the most important thing, I guess, on the desert island. So, yeah, that is a good question, though. But all right, anyway, so let's get back to this chapter. So we're done basically with our discussion of arrangements and the factorial operator, but we'll need the factorial operator for the next two concepts that we'll be defining. So once more, the formal definition of the factorial operator, one more time, is, and here you can see all you have to do is just multiply each number by its previous integers, and you'll get the number you're looking for. This can be used to calculate the number of arrangements of a set of n objects. Now, what if we don't want to take the entire group of objects and rearrange them, but instead we want to choose objects from a larger group? In other words, if we want to pick, let's say you go to the store and they have a lot of vegetables to choose from and you just pick a few of them, we may want to know how many different ways there are to choose them, given the number of objects that are available and the number that we need to choose. So what happens here, though, which is really important, we're choosing a collection of objects. Let's say we have n to choose from, and we want to pick r of them. The key detail here is that each way in which we choose these objects is considered to be a unique choice. The order of the choice matters. In other words, if I pick, just as a quick example of this, suppose that I have available to me, let's say that I'm going to pick, for some bizarre reason, I'm going to pick a license, create a license plate. No, where do you live? Upstate. Oh, how far upstate? Oh, I see. All right, I know that area a little bit. Wow, really? It's snowing. It's raining here. I'm in Danbury, Connecticut, which is not that far north of Purchase. Yeah, that whole area. That's part of that. I think I can't remember what it was called. There's a name for that whole corridor that runs across upstate New York from Albany over to Buffalo. I thought there was a name for that region of the state, but I can't remember anymore. But it's cold. It's all cold. Everything from Albany due west to Buffalo, all across Route 90 there, that's all cold territory, very cold. Yeah. But anyway, so imagine that there's a state where you're going to create, oh, what happened? You're going to create, you're right in the area. Yeah, okay. Well, Albany is a pretty cold little city, isn't it? Yeah, that's what I've heard. Huh. But anyway, let's say that for some reason, now this is a tiny little state, and you're going to create a license plate by choosing two letters from 5. Let's say for some reason, you're only allowed to choose from the letters A, B, C, D, and E. Okay, now, what choices do you have? What or how many, let's put it this way, how many choices do you have? All right, so imagine you live in a state where the license plates just all have 2 letters on them, but you're only allowed to choose from A, B, C, D, and E. Well, let's see, what can we do? We can have A and B, AC, AD, AE. Now, this is okay. And then now this is interesting here because I can have BA, BC, BD, BE, whoops, BE. I can have CA, CB, CC. No, I'm disallowing for repeated letters. I forgot to mention that. 2 letters from 5, and in parentheses, none may be repeated. Okay, that's the other rule too. You can't have 2 A's, for example. Okay, so CD, CE. We can have DA, DB, DC, and DE. And then we should have EA, EB, EC, and ED. Now, the key detail here that I want to point out, and you can see altogether there are 20 possible choices. Now, what I'd like to point out here is that I've got AB and BA as 2 separate choices. I also have, there's a lot of them. I've got AC and CA, even though they're both the same letters. AC and CA, even though they both have the same letters, because the order is different, these are considered to be 2 distinct choices. So formally, these choices, since the order of selection matters, each choice is formally known as a permutation. Okay, a permutation means we're choosing objects from a larger collection in such a way that the order of selection makes a difference. In other words, here with the license plates, we will distinguish between A, B, and BA. They'll be considered 2 different license plates. So the selection matters. Now, also, if you notice, I'm not taking all 5 of the original letters. If I were taking all 5 of them, that means I'd be looking at arrangements. But because I'm only picking 2 of them, we're going to call these permutations. Okay, now, here's the big question. Is there a way that I can create a formula that makes it unnecessary to count every single one of these choices? Because obviously this could get very big in a hurry. Imagine if I allowed us to choose from the entire alphabet. We could be here all day writing out all the number of choices we have. So instead I kept it down to 5 because I knew that even with 5, there'd be a fairly large number of possibilities. So we've got 20 choices when we choose 2 letters out of 5 where the order matters. Okay, so just remember, each one of these choices is called a permutation. And it turns out that the formula that we'll be using to calculate the number of permutations is based on the factorial operator. Okay, it'll come in handy one more time to help us figure out how many permutations are possible when we select objects from a larger collection. Now, here's another a good example. How about this one? This one hits a little closer to home. Suppose that the students of SRNY Purchase decide to start up a math club. There are 10 members of the club. We need, according to the rules of the school, we must have a president, a vice president, and a treasurer to have a proper club. Okay, they won't approve it unless we have all 3 of these officers. And they will be assigned at random. Suppose that nobody feels strongly enough that they must be the president or the vice president or the treasurer, but instead everybody agrees that we can randomly pick names out of a hat and assign the jobs that way. So everybody in the group gets a number assigned to them from 1 to 10. and we literally pick the three numbers at random. The first person that we pick will be designated the president. The second will be the vice president, and the third person we choose will be the treasurer. So let's just say that I choose the numbers 3, 1, and 7. And by the way, if you notice here, I can't repeat the numbers. I can't have student number 3 be both the president and the vice president, for example. So with these situations, we have to keep in mind that the one thing that we're not allowed to do is choose the same object twice. Okay, so we have numbers 3, 1, and 7, which means that whoever is number 3 is the president, whoever is number 1 is the vice president, and whoever is number 7 is now the treasurer. So here's the key thing, though. What if I'd chosen the same 3 numbers, but in a different sequence? In other words, imagine if instead of 317, I had chosen 731. Now this time, student number 7 is the president, student number 3 is the vice president, and student number 1 is the treasurer. So you can see that even though 317 and 731 are the same numbers, the order in which I chose them does make a difference. It determines who's doing which job. So both of these, 317, yes. Each of these choices, in other words, when I say each of these choices, I mean 317 and 731 is therefore defined as a permutation because I'm choosing objects from a collection in such a way that the order matters. So here we'd like to know, again, how many ways could we have filled these positions? Well, in this case, the number is starting to get pretty big. We may not want to write them all down, although we certainly could. So luckily for us, there is a formula. And the formula, as you'll see, is defined in terms of a range of, of the factorial operator. And so here it is. After all that buildup, this is the formula for calculating permutations. So the P there represents permutations. These two numbers tell me that we have a collection of n objects to choose from, and we choose r of them. Okay, the only constraint here is that r has to be at least as great as r. In other words, you can't choose 8 objects from a collection of 5. So n is the larger number, r is the smaller number. We're choosing r from n in such a way that the order matters. And you can see the formula is pretty straightforward, and it's entirely based on the factorial operator. And I think you'll agree this is a lot quicker than just writing everything down and listing them all. So for the students and the club, how many ways can we arrange, or how many ways can we fill the officers for that club? Well, in that case, we have 10 students to choose from, so n would be 10. And the number of positions that we have to fill is 3, so r would be 3. So you can see, yes, n is 10 because there's 10 students in the class to choose from. R is 3 because we're picking 3 students to fulfill those positions. And if you plug in the numbers, you can see that what you've actually got here is 10 factorial. This one obviously simplifies to 7 factorial. And if you plug those into your calculator, in fact, why don't you do that right now and confirm that this is correct? You'll have 720 different ways to fill these positions. So in fact, you know what, I'm going to get out my calculator and see what is the quickest and most painless way of doing this. I think that all you have to do is type 10 with a factorial operator and then hit the division sign and then hit 7 factorial and then equals. Yeah, that does it. All right, so in other words, you'll have 10 followed by the factorial operator, and then just hit the division sign, and then you can type 7 factorial, Then this time you will need the equal sign, and that'll do it. 720. All right, did everyone get that? Excellent. Now, how about for the license plate example? Okay, so for the license plate example, N equals 5 and R equals 2, because remember, we're picking 2 letters out of 5. So here's how this would work. NPR, or 5P2. So remember how this works. It's N factorial over N minus R factorial, 5 factorial over 5 minus 2 factorial, equals 5 factorial over 3 factorial, which is 120 over 6. And there you go. Just as we showed when we wrote them all out, it's equal to 20. All right, we all caught up. Now, in the next example, we've got a horse race. And what's happening with the horse race is that the way they do this is that the horses, you have all these horses, they run around the track, and what really matters is who comes in first, second, and third. They're typically prizes for whoever correctly guesses the winner, the person who comes in, the horse who comes in second, and the horse who comes in third. So the key detail here is that there are 8 horses numbered from 1 to 8. If I bet on 1, 2, 3, let's say I buy a ticket that says 1, 2, 3. This means that I'm betting on horse number 1 to finish first, horse number 2 to finish second, and horse number 3 to finish third. A person who buys this ticket is betting on horse number 2 to win, horse number 3 to finish second, and horse number 1 to finish third. So these are, even though they're the same numbers, you can see the order of selection matters. These 2 tickets mean something very different. So therefore, each of these choices, each bet, I guess we could say, is a permutation. And therefore, we should be able to figure out how many different bets we can place on this horse race with 8 horses. So in other words, we need to know, it would help us to know when we decide what to bet on, how many different outcomes can there be. All right, so in this case, N is 8 because there's 8 horses and we are going to pick 3 of them. And so using the same approach we did a minute ago, NPR is defined as N factorial over N minus R factorial. So yeah, and you can see here I've written it from left to right because this is, obviously when you're typing, you can't do a proper division like this, but we'll have 8 factorial over 8 minus 3 factorial, or 8 factorial over 5 factorial. 8 factorial is 40,320. 5 factorial is 120. So what we're looking for here is the ratio of these two. 40,320 is now divided by 120, and that turns out to be 336. Okay, that's a lot. That's still a lot. All right. Now, up to this point, we've considered arrangements where we take all the objects and simply change the sequence in which they appear. That, of course, can be calculated. The number of possible arrangements is calculated directly with the factorial operator. Now, we've been looking at cases where we're choosing objects from a larger group in such a way that the order matters. And we have a formula for calculating how many ways this can happen. Now, there's another possibility. What if we're choosing objects from a collection in such a way that the order of selection does not matter? That can happen as well. Okay, there could be cases where the order in which I pick the objects has no meaning. And so therefore, we need a new name to describe these choices. And these choices are referred to as combinations. So again, this is a collection of objects, or this is a combination is a selection from a larger group in such a way that the order does not matter. So let's think of a good example of this. I have one in mind. Let's try this case. Let's say that you go to a local Haagen-Dazs. I like this example a lot, even though it's early in the morning. It's never too early for ice cream. As an example, you show up at your local Haagen-Dazs, and let's just say they're having a promotion. I think that's how it's spelled. Let me just double check that. No, there's an S at the end there. Okay. You know, the funny thing is when the company first, I think it's a Danish company. No, I thought, wow, well, that's interesting. It says here that it comes from the Bronx. Wow. Well, they really know what they're doing, because I remember when they first came out, they were constantly promoting themselves as, wow, we're hard to pronounce, but we're so worth it. You know, in the early days when nobody knew who they were, this might be why they chose this weird name, because they knew that it would stick in your memory. Like, what is that? Haagen-Dazs. It's not like Ben and Jerry's. You couldn't possibly not be able to pronounce or spell Ben and Jerry's. But on the other hand, of course, Ben and Jerry are two real people. So that's why they picked that name. I wonder how they decided to do Ben and Jerry and not Jerry and Ben. Well, I bet that was an interesting conversation. But anyway, so Haagen-Dazs, of course, as you know, is a really top of the line ice cream manufacturer, and they have stores all over the place. But let's say you show up there one day and there's a special promotion. What is that special promotion? That might be. I have a feeling that's exactly what they decided to do, just to keep their friendship going. They probably just said, you know what, Ben comes first, so let's just stick with Ben and Jerry. I guess Jerry was on board with that. Yeah, and they're still alive as far as I know. You see them on TV, still not very often. They used to be on TV all the time. I believe that the company started in Vermont, and it took a while to catch on. At first, it was only available in New England. Now it's just everywhere. And the way they made their name is to have the really interesting flavors, like Cherry Garcia and that kind of thing. Nobody else had flavors like that. They were the first, and they kept the quality very high, which is another big selling point. So they really hit on the right formula, and they also their timing was perfect as well. But yeah, those two guys, they're just Ben and Jerry, good old Ben and Jerry, but they're crazy rich now. But anyway, so there's a special promotion. You may choose any 2 of 5 available toppings for free. Okay. So let's say you go up to the store, you're in the mall, and there's their Haagen-Dazs, and you say, all right, I'll take an ice cream, please. And they show you where all the toppings are. And they have, for example, let's say gummy bears, and then they have Oreos, and then they have marshmallows. What else might they have? Sprinkles. And God, what else might they offer you? Wow, I'm out of ideas. Who's got an idea for another topping that doesn't start with one of those letters? Reese's Pieces. There you go. Perfect. Reese's Pieces. There's another, you know what's interesting? There actually is a TV series on cable TV that all they talk about is the history of the different foods that we buy without on a regular basis. Like, for example, there's probably an episode where all they talk about is Reese's Pieces and how they were invented and who invented them and the entire history. I can't remember the name of the show. Oh, now I know what it is. If you're interested, it's called Modern Marvels. And that's what the show is about. Like one week it might be Hershey's, and the next week it might be M&Ms, and the next week it might be Wise potato chips. And basically it's all about how these products came to market and the history, and they're usually very, very interesting. But anyway, so we got the 5 toppings. Now here's the big question. Unlike the case with the horse race or the officers for that math club, does it make the slightest bit of difference what order you select your toppings? They're just going to get dumped on the top of the ice cream anyway you choose them. So I think you'll agree that each choice that you have available to you could be defined as a combination now, because the order in which I select them doesn't make any difference to the taste of my ice cream. So then when we go to make a list of all the possibilities, I'll use, of course, the first letters: gummy and Oreos, gummy bears and Reese's Pieces. We could have gummy bears and marshmallows, gummy bears and sprinkles, Oreos and Reese's Pieces, Oreos and marshmallows, Oreos and sprinkles, Reese's Pieces and marshmallows, Reese's Pieces and sprinkles, and then finally we have marshmallows and sprinkles. So unlike last time, if you notice, I have GO. I do not, whoops, it's not what I meant to do. I do also not, I don't also have G and O over, I'm sorry, O and G. Okay, in other words, I don't need to also list O and G because they're the same thing. Gummies and Oreos, Oreos and gummies. It means the same thing. In this case, the order does not make any difference. So here, there's a lot less possibilities than when we had, or when the order mattered. So here you can see altogether, there are only 10 possibilities, which means there are 10 combinations that can be created. 10 combinations can be created from when choosing two toppings from 5. Okay, because the order doesn't matter, there's only 10. Remember before when we had permutations with the letters and the license plates, we were picking 2 letters out of 5 as well, but there were 20 permutations. Because we had to list each one separately, the order mattered then. So we would have needed to have, for example, OG or RO, for example. Here we don't need any of those extras. We don't need to duplicate anything. So therefore we have 10 combinations only. Now, of course, that was still a lot of work to write them all down. We don't want to have to go through that every time. So it would be nice if there was a formula we could use. So let's see. Why don't we see if we can find ourselves a formula? Oh, here we go. There is a formula. Now, you notice what I've done here is I've also written directly below it the permutation formula so you can see how they're different. There's only one small difference. In the combination formula, you notice this extra term in the denominator. We have that extra r factorial, which basically splits out all the repeated choices. That's why it's there. So the formula looks a little bit messier, but remember, this is the one we use when there's only, when we do not care about the order. So why don't we try that with our gummy bear, our toppings example. Let's see, I'll sneak that in right here. So for the toppings example, so we had 5 toppings to choose from, and we chose 2 of them. So how many combinations are there? Well, we already know the answer, but let's prove it. All right, hold on. All right, here we go. So NCR equals, now we're choosing 2 out of 5. So remember the basic formula, let me repeat it up here. Okay, so again, the difference now is that extra R in the denominator. So this will be a little bit messier, but it won't be too bad. Okay, so now as you recall, just a quick reminder, 2 factorial equals 2 times 1. 3 factorial is 3 times 2 times 1. And 4, of course, is 4 times 3 times 2 times 1. So finally, 5 must be 5 times 4 times 3 times 2 times 1, which is 120. So we'll have 120 over 6 times 2, which is 120 over 12. And what do you know? Just as we predicted, it's 10. So there are 10 ways we can choose our 2 toppings out of a grand total of 5. Okay, so that was interesting. Now, here's a fun example for speaking of cards, which we had earlier, of course. What about a game like poker, draw poker? You've got a standard deck of cards, and everybody in the game is dealt 5 cards. Now, if you know anything about the game, it doesn't really matter, but the order of the cards in which you receive them doesn't have any bearing on the value of your hand. Okay, that's of no consequence. So that means that each hand that you are dealt could be thought of as a combination. In other words, you're picking 5 cards out of 52 in such a way the order is irrelevant. So now we'd like to ask ourselves, how many different hands can be dealt from a deck of cards? Okay, so in other words, we're actually picking 5 out of 52 objects in such a way the order does not matter. So we can think of each hand as a combination, and then we can therefore use this formula to come up with the correct solution. All right, so on the next slide, we'll see how this is done. Now, with the calculator, we're going to have to be a little careful here because you've got 3 things going on here. You've got in the numerator 1 expression, and then in the denominator, you have 2. Let me see what your best choice is here. So we already know the numerator 52. We saw that in the video. 52 factorial is a monstrously big number. So I think if you do this, 52 x factorial divided by open parentheses 47 factorial times 5 factorial close equals, I think that will do the job. Let me just confirm that. 52 divided by open parentheses 47 factorial times 5 factorial close equals. Yeah, that did it. Okay, so if you follow that sequence of keystrokes on your calculator, you'll get 2,598,960. That's a lot. Okay, I think you'll agree that's a large number. All right, but wait till you see this one. Well, let's try one more of these because this is so much fun. I think you'll agree this is kind of a fun application. In fact, what I'll do is I'll have you tell me the answer before I show it to you. All right, here we go. Now, you may have heard of this, maybe not. There exists a game called 3-card poker, which is the same as traditional draw poker, except that everyone gets 3 cards instead of 5. How many hands can be created? How many hands are possible in this game? All right. So what I'm going to do is give you a minute to think about this. And I'll quickly write back up at the top here the formula. And it should be clear that because the order of the cards in the hand does not matter, these are clearly combinations. Okay. And of course, also n equals 52 and r equals 3. So we'll have 52 factorial over 52 minus 3 factorial times 3 factorial So you can implement it on the calculator. In the following way. So who's got a number? Here we go. All right, we got some 22,100. That is exactly correct. 22,100. Perfect. All right. So hopefully, if you didn't get that, try it again. You may have made a typo on the keyboard. Let's see. Yeah. So just try that again, and you should come up with 22,100. Okay. So I think we kind of get the idea of combinations. We get the idea of permutations and arrangements. So those are the three that we learned in this section. Combinations where the order does not matter, permutations where the order does matter, and arrangements where we're taking the entire set of objects and just changing the sequencing. So what I've got now to tie this all together is a video. Woohoo, another video. All right, so let's check this one out and see what this one is all about. All right. All right. How was that? No, it was pretty good. I mean, I thought he did a good job, especially when they had all the pictures of all the choices, the pizza toppings and the ice creams. That was very interesting. Now, there is a follow-up video here by the same people. I think that we may as well watch it because we've only got 15 minutes left anyway. And this will tie together, although I have a feeling that we've probably shown these out of order now, but that's okay. We're going to get everything done. By the time we're done with both videos, we'll have a complete understanding of both combinations and permutations. So why don't we check this one out too? Because obviously if it's the same company that made both of them, it must be very good. So let's check this one out now. And then we'll be experts on this stuff. All right. Hi, welcome to Code Math. Okay, are we all done? Now, I just want to leave with one final idea here. And he didn't specifically, yes, I thought these were well done. He didn't specifically address this, but here's an interesting paradox. If you look at a combination lock, you know, the traditional one, the one you hang on your locker in high school, and it's got the wheel and it's got all the numbers. Suppose, and they usually have 3 digits. Suppose that you choose for your combination 1, 3, 5. If you spin the numbers 5, 1, 3, will it open for you? No. So that means that each choice that you make on this so-called combination lock, each choice, because the order of the numbers matters, is actually a permutation. So that means this thing should properly be called not a combination lock, but a permutation lock. So somebody screwed up when they chose the name for this lock, because each choice you have is actually a permutation. Okay. So that's something he kind of danced around it by, you know, like if you notice a couple of times he referred to the combinations in quotes, because each one of these choices with this lock is actually a permutation. And so there, now you know that combination locks are not correctly named. They should be called permutation locks. Okay, I just thought you'd find that interesting. So anyway, so we're done really with our discussion about what we've been calling this whole area. I think I mentioned in the beginning was part of a branch of mathematics called combinatorics, which is the science of counting. With all that background, now next time we can address or introduce ourselves to proper probability theory itself. And probability theory is a fairly complex framework, but we will be looking at some very interesting applications of it. And I think you'll find it extremely interesting as we go along. But this first part was meant to be background for what will follow. But I think you'll all agree that this was pretty interesting material. So anyway, so between now and I guess Monday, all you really have to do is make sure you understand what we've been doing. And I'll see you all on Monday.
Thank you.
Okay, see you next time.
Thank you. Have a nice day.
Okay, all right, bye.